All right. Now that we've talked about everything we can with balanced forces, we're now going to move on to the general unbalanced case. So, Newton's first law applies whenever there's an object moving at constant velocity, which means an object that's at rest or that's moving with a constant speed in a single direction. And in that case, the forces must balance. So, constant velocity occurs if and only if all the forces are balanced. Newton's second law describes the general case where there's a non zero net force exerted on the object. I like to state Newton's second law in words as an object accelerates in the direction of the net force exerted on the object, but we will always use it in equation form where the acceleration of an object is caused by there being a net force, and that acceleration is inversely proportional to mass. And that encodes the fact that mass represents this sort of inertial mass that represents an object's resistance to changing its velocity. So, increasing the net force on an object will increase its acceleration, and an object with more mass will accelerate a lower amount under the same force, and that's just another way of thinking about inertia. So, we got our small crate and our big crate under the same force F. We see the bigger crate will accelerate less under that. Now, this equation is also rearranged as F net equals ma. We'll do that when helpful, but realize that the more fundamental relationship is accelerations are being caused by net force. So that's why I like to write it like this. All right, we have a cannon, very professionally designed cannon here. Thank you to my art department, me. A cannon of mass 10m fires a ball of mass 1m along a frictionless surface as shown. Compare the magnitude of the force each object exerts on the other. That's our first thing. Then we're going to look at acceleration, and then we got to compute something. Okay, well, I really can just stop right here, right? The force each object exerts on the other. What does that sound like? That is absolutely just Newton's third law. Anytime objects interacting, forces exerted on the object are equal in magnitude and opposite in direction. So, uh, mutual forces are always just a Newton's third law pair. Cannon exerts a force on ball. Ball exerts equal force with opposite direction on cannon. What about the acceleration? Well, we just said that the force was the same. Acceleration is defined in terms of forces as the net force exerted divided by the mass. And we just said this net force is the same because it is a Newton's third law pair that is generating that net force on each object. So, according to this equation, same force, the bigger mass will accelerate less. So the cannon accelerates less than the ball because the can has more mass. Can has more mass or more inertia. So how do you say that qualitatively? A larger mass has more inertia, and thus it accelerates less under the same force. How much less? Let's determine that acceleration. So we want the ratio a cannon divided by a ball. Again, I really want us to think multipliers, so I'm always going to write this with multipliers. So for example, I can say that a of the cannon is going to be equal to the force exerted on the cannon divided by the mass of the cannon. So for my ratio type questions, the first step is get some sort of derived expression and then start doing multipliers. So A of the ball, similarly, would be F divided by its mass. So what is true about the force? Well, the force exerted on the ball will be the same, so you get a times 1 for the multiplier. And then what about the mass? Well, the cannon has mass 10m and the ball has mass 1m. So the ball mass would be 1/10 of the cannon mass. So that means that a ball would be equal to 1 divided by 1/10. So that 10 swings up to the numerator because you have a double division. So A ball would be 10 times A of the cannon. So that means that the ratio that we want, the cannon acceleration divided by the ball acceleration, is going to be just 1/10. Maybe I should show that rearranged, because we'd get, if we divide both sides by the cannon acceleration here, I'll move this up just to show that. You can probably reason why that's the case because we have that factor of 10, but I just want to show it explicitly. So if we divide the ball acceleration by the cannon acceleration, by dividing by the a cannon on each side here, we would end up with 10. So that means if we want the cannon ratio on top, we just flip both sides upside down. So we'd get AC over AB equals 1/10. Now, of course, you don't have to do this with the multiplier method. You could also just do this explicitly. I always like to show both ways at first, and then I'm just going to do multipliers only. So if you like to just plug in, we could just evaluate the quantity A cannon divided by A ball. So A is F over M, so I could do F over M of the cannon, which is 10M, and then F divided by the M of the ball, which would be 1M. So I would get everybody brings an F, and everybody brings a 1 over M. So I'd get 1/10 divided by 1, and I do get 1/10. So that's how you do it, just with the symbols. If you like plugging in symbols, I am usually a multiplier person. All right, suppose we increase the cannon mass to 100 m. Assuming the force exerted on the cannon remains the same, what's the new acceleration in terms of its original? Well, we know that A of the cannon is just the force exerted on it divided by the cannon's mass. So what happens now? Well, we said the force is the same, but the mass goes to 100 m. So if it was originally 10 m and goes to 100 m, that would be a multiplier of times 10. So the new cannon acceleration is, again, 1/10, except now it's a 10th of the original. So it'd actually be a 100th of the acceleration of the ball. Now that mass ratio is 100. So that's just really getting over this idea that, once again, forces are equal and opposite, but the cause being equal, which is the force, but the effect, the acceleration, is definitely not the same because of that inertia difference. Now we have a pretty common intuition type question about what forces do. So we have a rocket moving to the right in empty space, meaning it is just drifting there. There are no forces on the rocket. And we're saying that at any point, the rocket can turn on the thrusters and there will be an upwards force on the rocket. And we're going to draw the path taken by the rocket. If the rocket does not turn on the thrusters, the rocket turns on the thrusters briefly, then shuts them back off, or the rocket hits the thrusters on and does not turn them off. So the easiest case is we know that it says the rocket is just drifting to the right. So it is going to have an initial velocity to the right. And Newton's first law says that if there's no forces on the object, no unbalanced forces or no forces at all, the object's velocity can't change. So if there are no forces exerted on the rocket will continue just to move in a straight line forever. Then what happens if the thrusters are briefly activated as the rocket passes point P before being turned off? So what this means is that at point P, the rocket is going to get a brief push up. There'll be a brief push up, and then the push stops. So when the thrusters are activated, the rocket is going to get pushed up, and its velocity is going to change in the upwards direction, but then it'll stop. So what does that look like? Well, we're assuming it's very brief. So if there's a force up, we know the rocket's trajectory is going to end up turning upwards. And it's not going to go directly upwards because that would mean that something canceled its rightward velocity, which did not happen. So it maintains its horizontal velocity, but is given an initial vertical velocity at that point as well. So this is going to be a straight line path that is up and to the right. Now, what if we turn on the thrusters and keep the thrusters on? So, how is that different? Well, instead of giving it just a single push, we keep pushing it up and up and up and up and up. So, yes, it's going to maintain that horizontal speed or velocity, but it's getting more and more and more and more vertical speed. So, actually, going to make a curve because, yes, it continues moving to the right, but more and more and more and more of the velocity gets directed up. So, after a long time, the velocity would approach the y-axis as its direction because the vertical velocity is that much bigger. So this is a very common conceptual question that we see a lot. Kind of in a similar vein, where we have an initial and final velocity of an object, and we want to figure out which is the direction of the average acceleration and average net force exerted on the object. So we know that there has to be a force exerted on this object because the velocity will be changing. And if the velocity changes, the forces aren't balanced, so there is a net force, so there is an acceleration. Now, we can determine the direction of acceleration because we know that acceleration is the change in velocity divided by the change in time as a vector. So we can just do some tip to tail addition to figure out what had to happen. So our initial velocity, v0, was up and to the right. And our final velocity, vf, was left. I'm drawing it like this because we know that the final vector always points from the starting point to the ending point. So we have to ask ourselves, what vector do I need to add to the blue vector to end up at the green vector? Or essentially, how can I use a vector to get tip to tail addition to end up at vf? Well, we just connect them. So my acceleration would be this red line. This would be our delta v. So it's not acceleration, it's delta v, but it will be the same direction as acceleration. So our acceleration would be down and left. And Newton's second law says that acceleration and net force always have the same direction because net forces are what's causing those accelerations. So that is also down left. So all we did here is we just reversed our sort of method for tip to tail addition because if you know where you started and where you ended up, we can fill in the gap to get our delta. Another way of doing this without explicitly doing the geometry is saying that I originally started going up and to the right, and I ended going left. So I needed, first of all, I needed to go left because the right got turned into a left. So I know I have an acceleration to the left because right turned into left. So that would be a change left. And then also, I would need a change down because up went to 0. I went from up to nothing. So the up had to have been canceled out by a down. That's how you could reason that, which is what I went through in the text. It's definitely easiest just to do tip to tail. So when we're problem solving with unbalanced forces, we can take some more steps than we've had access to in the past because they're more interesting problems. So, of course, we start with a free body and we determine what the direction of the net force is. It will usually be accelerating in exactly one direction, and it's usually not the vertical one when we're on flat surfaces, meaning that even when we have unbalanced forces, usually they'll still balance in one dimension. So we can do that to determine things like the normal force or any other balancing forces. Then we write what's called a Newton's second law equation instead of a Newton's first law equation for the unbalanced dimension. So I like this formulation as net force, where I define the net force as the forces that help the velocity minus the forces that oppose the velocity. And why I like this is this form, when dealing with equations, helps when forces are competing. So I make all forces that drive the system in the positive direction positive, and all forces that oppose the velocity is negative. So I do that by defining positive as the way the object currently moves. Then you can use net force to get acceleration, and once you have acceleration, it is usually constant. And constant acceleration means it's time for the big four. So lots of these problems, the reason we do forces is because forces get us acceleration, and acceleration gets us literally everything we can want because we can link it with kinematics. So let's try that. A group of students want to calculate the mass m of a cart accelerating from rest. They pull the cart across a frictionless surface with a constant net force of 0.6 newtons. So we are given that the net force is constant and it is 0.6 newtons. The students record the displacement d of the cart as a function of time, as shown in the table. And we're going to begin by drawing the forces exerted on the cart. Well, of course, the cart exists on Earth. And since the cart exists on Earth, there is a gravitational force down. Cart is not falling into the center of the Earth, so there is a balancing force, and it's the normal force in this case. And then it's being pulled to the right. So there will be a rightwards pull, which I'm just going to call it F pull, because F net is not an actual force. So I don't want to call that F net on my diagram. I'm just going to call it F of the pull. And we can stop. So this would not be allowed in the balanced force world, but this is not balanced. So we don't need anything to cancel the pull. So it says determine the magnitude of the cart acceleration in terms of F net and m. Well, by definition, Newton's second law tells us that acceleration is net force divided by mass, and that's it. Because F net is the pulling force. So this is literally just Newton's second law. Derive an expression that relates t and d to m. So we have arrived at this fact that acceleration equals F net over m. And we would like to somehow get a relationship that relates d and t to m, because we're interested in this mass m. Again, F net is known, so this can show up anywhere in my equation, because at the end we're just going to plug in 0.6 newtons in for this object. So the key here is that we have no acceleration data. We're only given d and t. So that means we just need an equation that involves d and t that we can get rid of an a in. And we did say that once you have acceleration, it's kinematics time. So the cart is being pulled from rest. So these are our laundry list variables. So delta x, we do have that. Delta x, this would be the distance d. We start from rest. Doesn't look like we know the final speed, and we probably don't want it. Acceleration was F net divided by m. And then time was also known. Time is just t in the data table. So notice we have our three things, right? Kinematics, we need 1, 2, 3 things. So we can relate them with an equation. And the VF-less equation is delta x equals 1/2 at squared plus v0t. So that would give us d equals 1/2. A was F net over m t squared plus 0, v0. So our derived expression, I think we'll move the 1/2 inside. D would be F net over 2m times t squared. Now we can check that this is valid, because for any of these best fit questions, we should have an equation that relates your x and y variables in your table, so something with a d and a t in it. And also, you should have the unknown quantity and everything else should be constants. So again, remember, we do know F net. It is 0.6 newtons. So how are we going to linearize this? Because it's not linear, we have a square. We just graph d and t. We know that accelerated motion does not make a straight line. So we would have gotten a concave up curve, so we got to linearize it. Now, this is one that we've seen before, just not with forces. So our equation was d equals F net over 2m times t squared. No problem with d. So that can just go on the y-axis. Now our other variable is t, and the t is being squared, so that is what's causing our non-linearity. Tricky one. So I'm going to banish t squared to its own box to become my x variable. And then that means that everything here better be a constant, and that will be my slope. And it is, right? Because F net is 0.6 newtons, and m is unknown, but it is a constant, and we want to find it. So we will plot d on the y-axis and t squared on the x, and the slope will be F net divided by 2m. So from the power of doing this ahead of time, the mining off camera occurred, and here is our best fit linearization. Again, very linear. Notice I squared all of my t's. I put those on the y-axis, or x-axis rather, and I plotted the regular d variable, best fit line, nice and linear, and then I Desmosed it just to get the slope. So we wanted m. So from the previous part, we identified our slope as being equal to F net divided by 2m. So that tells us 2 times m times slope would be equal to F net, or m would be equal to F net divided by 2 times the slope. And I think just this time, I usually don't do the units at all, and just sort of say give the units in what the quantity is actually measured in, but we'll show this one. So the net force was 0.6 newtons, and the slope would be 2 times, let's see, what's the slope? We said the slope is 0.8, we'll round it to. And the slope will be units of meters on the rise and seconds squared on the x. So this would say that our mass would have units of newtons per meter second squared. But if we remember actually how the newton was defined, we said a newton is a kilogram times a meter per second squared. So the meters per second squared cancel out, giving us kilograms. So I'll TI this, and I get 0.375 kilograms. Seems reasonable for a piece of lab equipment. I always try to put regular values in here. So that is that. That's a nice classic linearization. All right, now we have some angles. We have not the 3, 4, 5. This is actually the 5, 12, 13 Pythagorean triple. So this is the crate being pulled across a floor question, except now it's not balanced. So there is no friction. We haven't covered friction yet. That's coming later. We have 13 newtons of tension at this angle. We got to draw the forces. All right, well, of course, the crate is on Earth, so it has a weight mg. Then we will pull it with a tension force. See, how do I want this? Let's make FG longer so I can show the normal force better. That would be my FT. And then, yeah, this crate will accelerate horizontally. That is totally fine. We know there's going to be an unbalanced force pulling it to the right. But what's definitely happening is we're given, assume the crate maintains contact with the surface at all times. And maintains contact with the surface Anytime we have this fact, maintains contact with the surface, this means that we have a normal force. Normal force exists because it's there to balance. So we have 1, 2, 3 units down, and then we have 1 unit up. So normal force has to make up the difference, which would be 2 units up. Notice the normal force is less than mg because it gets some help from the tension. And that's it. But of course, we also like the component body for these types of problems. So our component picture looks like this, where we have a gravitational force down, we have a tension component, FTX, right? Tension component and scam crypto exchange platform, I guess. And then we have its FTY up, and then we have normal force up. So we can see what's balanced and unbalanced. So we see that we have the vertical balancing that happens here, and we have the lack of balancing that is going to happen in the x direction. All right, let's first find the horizontal and vertical tension components. So we know that this is going to be trigonometry. We have that nice horizontal angle, so it is just our usual sort of expected triangle here. Where this will be 13 cosine 22.6 degrees, and this will be 13 sine 22.6 degrees. Because again, adjacent, this angle touches the horizontal side, so that would be a cosine. The angle does not touch the far side, so that would be a sine situation. So 13 cosine 22.6 degrees, 13 sine 22.6 degrees. And I said this is a 5, 12, 13 triangle. And notice the 22.6 degrees, that is below 45. So that means our triangle is more flat than vertical. So the 12 side is going to be the horizontal leg because that is longer. Let's see how close this is. I know I always make it with rounding. Yeah, 12.00. Okay. What is the weight of the crate? Well, it's the weight, right? It's just mg. Mass is 2 kilograms, so the weight would be 20 after multiplying 2 kilograms by 10 Newton per kilogram. What's the normal force exerted by the crate? Well, we know that it's attached to the ground, meaning the upward forces and the downward forces balance. So there's a normal force up and part of the tension force up. And together, those balance the gravitational force down. How do we know that? Look at the component body, right? The component body is telling me what equation to write. So we don't know the normal force. We said the y component of tension was 5 newtons. And the gravitational force was 20 newtons. So the normal force is 15 newtons, which is notably less than mg. All right, what will be the acceleration of the crate? Well, we know that acceleration is defined as the net force divided by the mass. So who is supplying the net force in this scenario? Well, if we look at our component body, everything is balanced vertically. So the net force would be the winner, or the only force that's unbalanced, and that would be the x component of tension. So 12 newtons would be the net force. 12 newtons would be our net force exerted on the crate. Again, net force is not a force itself. It is always supplied by something else or a difference or sum of other forces. In this case, the x component of tension is supplying that. So our acceleration would just be 12 newtons divided by 2 kilograms, which would be a very large 6 meters per second per second. Pretty large acceleration for a crate, but I used it to make something work out. So why do we find acceleration? Because that links every kinematics quantity. So once we have acceleration, we can do kinematics because we have a constant acceleration. Calculate the speed. So that's how I know it's kinematics. Forces only talk about acceleration. Speed, time, distance, etc. is kinematics. So, laundry list time. This is one thing that I will give props to the other countries on for sure. I like that they call these the Suvat equations. I like that. Where they call position S and V0U Suvat. But we're saying the crate is traveling 1.33 meters starting from rest. And we want the speed. And we do know the acceleration. So that's why we had to do the force analysis, because we did not have a third quantity. All right, so timeless. Kinematics without time is the squared velocity equation. So this means velocity final will be the square root of 0 squared plus 2 times 6 times 1.33. And you know that I picked that because it works out nice. See, what is that? 1.33 is 4/3. So that would be 4 times 4, 16 under the square root. So 4 meters per second. Cool. All right, now we'll look at the general case of this, where the crate is being pulled with a force larger than its weight. And in this case, there exists a maximum angle that you can pull at before the crate loses contact with the ground. So this is actually something I've ran into messing around with my free body diagrams, because you'll see that if you make this tension force too big, it'll balance gravity by itself, and you'll be left with no normal force, which means it's not in contact with the ground. So this is a very important scenario to know. Anytime you're talking about losing contact, that is a critical change that occurs when there is no normal force. So our vertical force balance looked like this, where the normal force plus the y component of tension together balance the gravitational force. We said in this limiting case, the normal force goes to 0. The y component of the tension force was just F times sine theta, because we did not have touching that angle, right? That's F sine theta. And Fg is, of course, mg. So we want to figure out what that angle theta is. And it makes sense it's a minimum angle because sine theta is the vertical component. So if you get bigger and bigger and bigger with your angle, it gets more and more vertical. So that's why the minimum angle, anything above that, you're supplying too much vertical force. So this would tell us that sine theta would be equal to mg divided by f. And then to undo the sine from each side, we have to inverse sine it, right? To get our angle inside, this would mean that theta would be equal to inverse sine of mg divided by f. Kind of gross, but there's our answer. Notice we actually needed f to be bigger than mg for this to work, because if not, we would get a argument of 1 or higher inside this, greater than 1 inside this inverse sine, which can't happen. And also conceptually, it should make sense, because if your force is not equal to mg, there's no way a component of that could balance mg by itself. All right, our last topic for just our standard Newton's second law will be this idea of reference frames again. So that was our second thing we did, is we talked about the idea where different observers are going to observe different velocities. Now, we've been doing all of our physics inside an inertial reference frame, which means for Newton's first law to hold, where if there's not a force exerted on an object, it won't accelerate. you need to be in a reference frame that is not accelerating itself. So, what can happen is if your reference frame is accelerating from some outside force, an object can accelerate and you can't be able to determine where it's coming from. So, for example, speed. If you're in a car speeding up, you'll get pulled back when the gas pedal is down, and you'll get pulled forward when the brake pedal is stepped on. Why does that happen? If you're in the car, you couldn't really determine who is causing that force on you. It's because your frame is accelerating. Now, there's actually a fundamental result relating to this known as the equivalence principle. This is an Einstein idea, and Einstein says that any sort of acceleration in your frame could be thought of as a gravitational field. So, when I'm accelerating in my car and I'm getting pushed sort of backwards when my car accelerates, that would be the same as if there is some sort of sideways gravity acting on me. So, an observer can't tell if there's just a gravitational field in their area or if their frame is accelerating, which is kind of trippy to think about. The same idea where there's no absolute motion. So, how we actually handle this is this idea of if your frame is accelerating, we can correct all the physics just by adding a additional gravitational field opposite the acceleration. Just like we had the reverse boost idea for the velocity changes, we can do the same thing. We'll show that in context, how that works. So another result of this is if your frame is accelerating, this is a common case where you will get the normal force exerted on you to not be mg. So the apparent weight is something that we will often call your scale reading. So if you step on a scale and you're at rest, well, we know that your scale reading is just going to be mg. So that's why bathroom scales are totally reasonable to use, and they do give you your weight most of the time. So when you're measuring your weight on a scale, you're not actually measuring your weight at all. You're measuring your normal force. So scales measure normal force, not weight. But why don't we make that distinction? Because no regular person is going to take their scale in a situation where the normal force is not your weight. So as long as you're not accelerating and not on a uh, angled surface, you will not notice that normal force is what's being measured. This should be clear that it's not actually the weight of the thing, because if I press on a scale, I can generate a huge force that's not the weight of my hand. So what can happen is if your frame accelerates, the thing that is causing you to accelerate is going to be the floor or the scale. So if I'm accelerating up, the normal force has to push even harder than normal or than usual to get me to accelerate up. Because if I have an acceleration up, there must be a net force up. And since my weight can't change because I'm still on Earth, normal force changes to account for that. Same thing if I'm accelerating down. If I'm accelerating down, there must be a net force down, so the weight must beat the normal force. So you'll see that you feel heavier or you gain weight when you're accelerating up, and you feel lighter or lose weight when you're accelerating down. And again, think of the extreme case of free fall, where there's just no force up. You'd feel weightless. That's what we'll talk about now. So the extreme case of your apparent weight, also known as scale reading, is weightlessness when there's no normal force. Because if I'm just accelerating down at g, that means the net force on me is mg. So there's no normal force. When you feel lighter, it's really because the normal force on you is getting lower. So let's do some elevator problems. So we have a person elevator car system of mass 500 kilograms. We have the elevator traveling up at 2 meters per second at constant speed. We have the elevator traveling up and speeding up at 2 meters per second per second. And we have the elevator traveling up and slowing down at 2 meters per second per second. So first thing we want to do is draw the velocity and acceleration of the elevator in each scenario. Well, we have elevators traveling upwards at a constant speed in scenario 1. So in scenario 1, the velocity would be up and the acceleration would be 0. I'm at constant speed. In scenario 2, I am traveling upwards and speeding up. And in scenario 3, I am traveling upwards and I'm slowing down. So remember, slowing down means that velocity and acceleration are fighting each other, so they disagree. So I have to have the same acceleration, but downward. So if we look at this scenario, we see we have 0 acceleration, upwards acceleration, and downwards acceleration. So now let's do a net force, or just a force diagram. So it is the same elevator every time. So we know that we should have the same gravitational force exerted on the elevator in all 3 cases, because what causes the weight? That would be mg, it's you and the planet, and neither of those change. But we must have different tension forces, so we do know that we're going to have a gravity down and a tension up, because those are the only, the cable's the only thing touching the elevator. So just to remind ourselves, we had no acceleration here, because we're traveling up at constant speed. Here we have upwards acceleration, because we're traveling up and speeding up. And here we had downward acceleration, because we're traveling up and slowing down. So this means that net force must be in each of these directions. So for there to be no net force, this is going to bother me because I like to make my tensions green. So what this means is that we need to draw the tension force in such a way that the net force is in each of these directions. So if there's no net force, then that just means the tension exactly balances the weight. If the acceleration is up, the tension must beat the weight. And if the acceleration is down, the tension must lose to the weight. So notice my net force would be 0 units, 1 unit up, 1 unit down. So let's rank the tension, justify your ranking. Well, it's pretty clear from this picture. Scenario 3 has the lowest tension. Scenario 1 has the middle tension. And scenario 2 has the greatest tension. So let's justify our ranking. Well, we know that mg, the downward force, is fixed, so the tension must be responsible for creating that net force or lack thereof. So to accelerate down, tension has to be less than mg. To not accelerate, tension must be equal to mg. And to speed up, going up, tension must beat mg. So that is exactly what I said here, right? Tension balances in scenario 1. Tension must be bigger than weight in scenario 2. Tension must be less than weight in scenario 3. All right, let's calculate the magnitude of the tension in the cable in each scenario, 1, 2, and 3. So scenario 1 is easy because this is the balanced one, right? The up forces equal the down forces. Tension up is equal to mg down. The mass of the elevator system was 500 kilograms times 10, 5,000 newtons. So this should be our middle value. All right, what about scenario 2? So we said that one way of doing these sort of problems is saying that the net force is the helping forces minus the hurting forces. So the net force would be the forces that help the acceleration or help the velocity of the system minus the forces that hurt the velocity of the system. You can think of it as speed up minus slow down also. So in this case, F net is always equal to MA. What is helping my system accelerate in scenario 2? Well, what is helping the velocity? Well, the velocity is going up. So tension is helping the velocity. So this would be Ft. And then what is hurting the velocity? Well, that would be, it's mg. So now we can just do some plugging and chugging. We would get, I think 50, right? No, 500. 500 is our mass. Our acceleration was 2 meters per second per second. So this gives us 1,000 equals Ft minus 5,000. So we can take a pause here and make sure this equation makes sense. So knowing the acceleration determines the net force, because F equals ma. And by plugging in, what this tells us is that the net force is 1,000 newtons, which means that tension must beat the weight by 1,000 newtons. So this tells us that the tension force is equal to 6,000 newtons. Now we can do the same thing. So we can do the same thing in scenario 3. We can write that our net force is still equal to the helping forces that help the velocity minus the hurting forces that oppose the velocity. So here, once again, we still have 500 newtons, but this time the acceleration is down. So there will be a negative acceleration. The tension force still helps. The gravitational force still hurts. So what this means is that the tension force now must lose to the weight by 1,000 newtons. So we get negative 1,000 plus 5,000, which is 4,000. Notice we have a nice symmetric problem because the accelerations were equal and opposite. So what I mean by that is the balancing tension was 5,000 newtons. So to accelerate upwards at 2 meters per second, you needed to beat that number by 1,000. And to accelerate down at 2 meters per second, you had to lose to that number by 1,000. So this is kind of tricky, these elevator type problems. I always like the help minus hurt situation where forces that are going with the velocity are positive, forces that are fighting or going against the velocity are negative. And in this case, the acceleration was negative because the acceleration is going opposite the velocity. All right, a person then drops a ball in the elevator. Determine the acceleration of the falling ball measured by the person in each scenario. So this is the equivalence principle, where we have to add a fake gravity field to the elevator in the opposite direction of the acceleration measured from the lab frame. This is the idea of getting pulled forwards or backwards in your accelerating car. It looks like a fake field is acting on you. So scenario 1, this was 0 acceleration. Scenario 2 was this acceleration. And scenario 3 was this acceleration. So what would a person in the elevator measure? Well, scenario 1, they would just measure 10 meters per second squared because there is nothing strange happening. So they would just measure a ball in free fall. So we're saying we drop a ball in the elevator. What acceleration do we measure? So how this is going to work is we drop a ball, and all we have to do is we have to add as vectors the real gravitational field and the fake gravitational field generated by the reference frame. So here, all of our frames are going to begin with our usual gravitational field. This is the real one. We can copy paste that twice, and then we'll adjust that. So remember, as with the velocity rule, the observer will measure sort of the opposite. So we have that reverse boost. So if the frame velocity is accelerating up, that means that our fake field would be 2 meters per second squared down. And by symmetry, it would be 2 meters per second squared up in scenario 3. So this would be our collection of real and fake gravitational fields. So this would be the real field, and our green one would be the fictitious or observed field. So what this means is that the person dropping the ball in the elevator would experience the ball going faster than g when they drop it in scenario 2, and they would experience or measure the ball accelerating slower than g in scenario 3. So we can conceptualize why this makes sense. Because in scenario one, you're just dropping a ball in a normal elevator, so you just measure G. That one's normal. In scenario two, yes, you're dropping the ball downward, so it would accelerate down at G, but also the floor is accelerating at you at 2 meters per second. So not only is the ball accelerating towards the floor is accelerating towards the ball, and they're getting closer together. So the 10 and 2 add together, resulting in a net field of 12 meters per second per second. And then in scenario three, yes, the ball would accelerate down at 10 meters per second, but also the floor is accelerating down at 2 meters per second, going away from the ball. So we get a lower field than if the frame wasn't accelerating because the ground is accelerating away from the ball versus towards it, as in scenario two. Oh, that is conceptually difficult. What a problem to end on. So this is just our basics of Newton's second law. Again, we can think about just this help minus hurt idea, but generally the good strategy is just draw your free body diagrams and create a net force equation, which is always the winner, right? Help minus hurt. Set that equal to MA.